All right, what's up, my sexy people? So, thank you for joining me in this live. So, in this live, we're going to do physics, and you should watch my chemistry series also, starting with the chapter one, because this is going to be an extension of chapter one. Everything I said in chapter one applies to here, because it wasn't until the Europeans came into Raza, where Raza stayed in our side of the ocean, that they discovered zero, and then because of that they were able to get calculus, which basically we're gonna start doing all that shit right here in physics. And the only difference is that limits and all that you need to probably go to math. I don't think we're gonna do a calculus series here. uh we're just gonna stick to chemistry and physics, but it's all just math basically. But anyways, we're gonna solve basically the universe, and that's all we're gonna do. The difference between mathematicians and people that study physics, chemistry, and like biology is that we need physical material in the universe, whether it's energy or matter. That's what we need. Otherwise, we wouldn't have a job. Anyway, so in today we're gonna start reading, but just keep heads up on everything I just said. So in this chapter, you should be able to do all that. You guys could just read that for yourself. See that? Okay. Oh, so anyways, this book has a little bit of a history. This is the preliminary one that I bought. Oh man, I don't know if I'm gonna be able to. Yeah, it's gonna be slightly dark right there. So fuck it. But anyways, is there too much glare right there? Huh. Anyways, I forgot what I was gonna say. But anyway, let's just fucking get started. Yeah, I forgot what I was gonna say. So, anyways, we're gonna start with chapter one. Oh yeah, so this book has a history. The professor gave me this book. It's not really a book; it's actually a preliminary book. It has holes because this is the one that they get a copy, right? Like they produce these, and then this is the one they edit and all that shit before they even make the book to sell to the students. You know what I mean? So I got the preliminary for free because I didn't have money to fucking buy the book. But uh anyway, so that's the history on this little exact book. It's not really a book. So here's my folder shit, you know what I mean? But anyways, we're gonna start physics, chapter one. So let's just get started, all right? All right. Sorry, I had to read sideways, so it's gonna be a little bit of a B word. Hold on. Let me see if I could. Yeah, that's not helping. Yeah, I was trying to see if I could help it a little bit, but I guess not. Oh, yep. A little bit. All right, so let's just start reading. So anyway, so thank you guys for joining to me in physics. So remember, join me in the chemistry and the physics. All right. So let's just get started. So chapter one. So physicists use a special language, part words, part equations to describe the natural world. Oh, so anyways, if you believe in the flat earth and all that bullshit, we're gonna what do you call it? You're gonna be able to calculate everything and judge for yourself whether the fucking all that shit for yourself. All right. So just as a heads up. Oh snap! My notepad. Hold on, guys. My phone closed up and I had the notepad. Hold up real quick. All right, let's go, baby. All All right, so let me, man, sorry, I have the computer in such a weird way. All right, so here's the notepad, full screen notepad, and the book. All right, so let's go, baby. All right, so I think that's all I read. A humming. All right, a hummingbird is a beautiful sight to anyone as seen through the eyes of a physicist. However, a hummingbird is a remarkable shit. Hold on. The hummingbird is a remarkable illustration of several physical principles at work. The beating of a hummingbird's wings pushes downward on the air, which causes the air to push upward in response and keep the bird afloat. Hold on, guys. Let me fix the mic real quick. There you go. Let's see if that's a lot better. All right. So the flow of the blood causes the air to push forward in response to keep the bird afloat. Wait, hold on. The flow of the blood through the hummingbird's body is governed by the principles of moving fluids, including the interplay of pressure and friction in the narrowest blood vessels. Sorry, hold on. Let me get something to read it, because it's hard. Like I said, I'm sideways, guys. The bending of light rays as they enter the bird's eye forms an image in the retina, providing. Hold on, guys. Let me get something to read real quick. I wonder if that would help. Not really. Damn. All right. So, anyways, let's try it. Oh man. I forgot how I had I think I had this chemistry book the same way, but it's whatever. Anyways, the bending of light rays as it enters the bird's eye forms an image in the retina, providing the hummingbird with vision and the subtle interference, some shit of light waves reflecting off the feathers at the bird's throat gives their characteristics incidents. I don't know. You got wait. Iridescence, some shit like that. You guys read that shit. A truly understand and appreciate hummingbirds or any other living organism, we need to understand the principle of physics. The purpose of this book is to help you gain understanding, man. And like the first chapter in chemistry, it's fucking boring, the physics, but it's not as boring as the chemistry one. Learning physics is somewhat like learning a foreign language. If you're paying a brief visit to a foreign country, you may just memorize a few key phrases such as where is a hotel in local language. But if you want to be fluent in the language, you don't memorize millions of phrases for the countless situations you might encounter. Instead, you learn the language by internationalizing a vocabulary of useful words and the grammar that allows you to combine those words into meaningful sentences. Using those basic tools, you can express an enormous variety of ideas, even those no one else has expressed before. In the same way, it may seem as the outset of physics is a long complication of rules, equations, definitions, and concepts. By taking a closer look, we discovered that it is a long list of physicists or physics phrases are created form a much smaller set of physical grammar and the vocabulary of physics. Your goal is to become fluent. Damn. And remember, guys, there's two ways to learn physics. It's you can learn it through the way we're gonna do it this way, or through waves. When I first learned physics, was learning physics through waves, but this is gonna be a little bit different. I mean, this is probably more chronological on how it happened in European history and right now in the global history also. All right, so let's keep reading. In physics, by understanding how to use rules of physics, grammar, to connect vocabulary of physics. The vocabulary of physics is often expressed in terms of mathematical quantities and the grammar that relates those quantities and the equations of physics. Like most physics, like most physics books, uh, this one contains many equations. Not all the equations are equally important. However, a much smaller set of fundamental equations express the key ideas of physics by starting with those fundamental equations and combining them to use rules of algebra. Uh, you'll be able to solve all the physics problems that you'll encounter in this book. Oh, it's tempting to view equations in this book, even in the fundamental ones, as a beginning all there is to learning physics. Beginning all there is to learning physics. Uh, if you adopt this view, you'll get the idea that solving a physics problem is simply a hunt to find the correct equations. Not so. Each Not so. Each of the equations in the physics is shorthand for a concept that can be much more profound than the equation one might suggest. For example, in Albert Einstein's famous equation, E equals mc squared, this equation E represents energy, M equals mass, M represents mass, and C represents the speed of light, which light travels in a vacuum. But the equation means it's, well, I thought that was a hair, but it's a it's a, what do you call it? A line from the book. Which means it's something deeper, in which book with often the fundamental equations which explanations attached as in this one. All right, so even though it's hard for me to be reading and all that, basically don't memorize the equations, guys. Instead, memorize like know the situation and everything that's happening in the situation, and you should be good. All right, and you should be able to solve everything, or at least get your get yourself in the right direction. Rest energy of an object equals E. All right. M is the mass of the object. Speed is the light of the vacuum is C squared. All right. The rest of the energy of an object. The rest of the energy of an object is the amount of energy it possesses simply as a consequence of having mass. Einstein was the first physicist to deduce that energy of this kind existed. Equation 1-to-1 shows the rest energy is directly proportional to the mass. The greater the mass of an object, the greater its rest energy, and vice versa. And the rest energy in many kitchens, and the rest energy of an object decreases as it must decrease as well. You can find an example of this in many kitchens. In a gas ranging, natural gas, mostly methane, CH4, combines with oxygen to produce carbon dioxide, CO2, and water, H2O. The chemical reaction takes place is CH4 plus 2O2 goes to reacts and forms CO2 plus CH2 solid. We already, so I don't think I really need to pull up the the booklet or whatever. Oh shit. All right, so this is what's happening right here. CH4. So you should guys should already know how to do this stuff because we already covered this. Plus 2O2 equals CO2 plus H2O. All right. So remember, there's a 2 and a 2 right there. All right. So that's what's happening right there. This process releases energy in the form of heat and light. The energy comes from rest energy. So the combined rest energy produces a CO2 molecule and two H2O molecules in less than rest energy of the reactants. A CH4 molecule and two O2 molecules. Equation 1.1 tells us that the combination of mass of the molecules present after the reaction is slightly less than the combination of the mass of the molecules present before the reaction. This is a remarkable statement, but sensitive measurements reveal it to be true. When you look at a flame in equation 1.1, itself isn't an important part of this story. This concept is behind the equation that is truly important. That damn, I don't know if I'm reading this shit right. This is an important idea that can be easy to forget when we come across an important idea like this one in a situation that requires special care. We put the watch out box like the one we left on the left side of this page. Watch out right here. All right, so hopefully I read that shit correct because it was if not, you guys just go back and read that shit. But it's hard to read shit sideways, guys, and I should probably just read it off the computer. All right, so remember, we're learning physics, and all you got to do is just keep following, and I'll do all the work, and I'll read the book for you. And if you want to go ahead, it's right there also. So 1.2, success in physics requires well-developed problem-solving skills. More than just broadening our understanding of the world, the process of learning physics involves learning to solve problems. Physics problems can appear challenging because they usually can't be done simply by selecting an equation and plugging in the values. And plugging in values. Solving the physics problems is easiest. However, hold on, guys. Solving physics problems is easier. However, if you build up the set of tools and techniques and then apply a consistent strategy, our strategy for solving problems involves 3 steps that are referred to as the setup, solve, and reflect. We'll use the steps in all the work examples of this book. All right. So there it's telling you how they're going to help you solve all that shit. If you want to go like there and look for yourself. I'm not going to read all that. So let's read, continue in the bottom and then flip the page. All right. So all right, learning physics. All right, learning physics will be easier if you study and many worked examples in this book and get the habit of following the same steps and set up, solve, and reflect in your own problem solving. Okay, perfect. All right, 1.3. Measurements in physics are based on standard units of time, length, and mass. To the average person, physics calls to mind speculative theories about the nature of matter and the origin of space and time. But at the heart, physics is an experimental science based on measurements of the natural world. Over a century ago, the renowned Scottish physicist Lord Kelvin, 1824 1907, expressed this viewpoint. If you can measure that of which you speak, and you can express it by a number, you'll know something of your subject. But if you cannot measure it, your knowledge is unsatisfactory. I believe this is now I was gonna say something, but never mind. I was gonna say something about the Kelvin, but I'm not sure if that's guy the same guy that they did the Kelvin scale crap. But you guys go figure that shit out. Any measurement requires a standard of comparison. For example, let me put the mic right here. See if I could do it better. Any measurement requires a standard of comparison. If you want to compare the heights of two children, for example, you might stand to compare the heights of the two children. For example, you stand them side by side and use the children's height as a reference for another, a reference for the other. A better and more reliable standard would be to use a vertical rod which equally spaced markings, in other words, a ruler that acts as a standard length. In physics, three fundamental quantities for which is essential to have standards of time, length, and mass. The standard units or the standards or units for these three quantities is seconds, meters, and kilograms, respectively. And the system of units is based on the quantities is called the Système International. I think it's some French shit, or SI for short. Système International, some international, some shit like that. Anyways, SI for short. By understanding how these standards are defined, we'll get a sense of precision toward which physicists strive in their measurements. Table 1.1 illustrates all the fundamental SI quantities, including others that we'll encounter in the later chapters. The definition of a second abbreviated is based. Hold on. The definition of the second abbreviated is based on the properties of the cesium atom, which when such atoms are excited, they emit radio waves of a very definite frequency. The second is defined to be the amount of time required for a cesium atom or a cesium to emit 9.192. Let me see what the number is. Hold on. Anyways, let me just. I'm just gonna tell you guys. It's 9192.631.77. Okay, so that's thousands, millions, billion. So I think it's 9,192,631,777. 770 complete cycles of these waves. This may seem like a bizarre way to measure time, but modern radio technology is highly refined as a relativity each to compare a gas of cesium atoms, which the right properties, hence a physicist anywhere in the world could readily repeat these measurements. All right, so basically what it's saying right here is that a second is basically dependent on the cesium atom. And if I get my chemistry book, or if you pull out a periodic table, the cesium or cesium, I don't know how you pronounce that shit, atom is defined as a 1 second when it emits that many. Let me tell you guys where I'm at. So when it emits this many was it light waves or some shit? Some shit about a waves, right? The amount of atoms excited they emit radio waves of a very defined frequency. So the radio waves it emits, so once it when you excite the atom, it emits these radio waves, and when it releases this many amount is defined as 1 second. All right. So everywhere in the international. Oh wait, I forgot to tell you guys. Before I tell you guys everything when we're reading right now, I believe the scientific standards have changed. So even though we're reading this, uh, the whatever is the standard has changed. But either way, it's still we're still gonna get the same answer. All right, a 1 second still 1 second, but the definition of something has changed. All right, because this book is but anyways, either way, physics hasn't changed much in the past 100 years. So, but I have to well, we all have to catch up on the how far are we on the scientific standard units. But anyways, just a disclaimer and something to be thinking about. All right, so in the past objects such as metal bars which were used to standard of length, these were not very good standards. Hold on. In the past, objects such as metal bars were used as a standards of length. These were not very good standards, however, because their length changes slightly, but measurably when the temperature changes. Basically, when you heat up things, they or cool things down, they kind of expand or contract. That's what they're saying. Today, radio technology is used to define the meter. Hold on. Yeah, today, radio technology is used to define the meter, abbreviated M, the SI standard of length. The speed of light in a vacuum is defined as to precisely 299,972, 458 meters per second. 299,792,458 meters per second. So that the meter is the distance that light or radio waves, which are form of light, travels in 1 over 200. That fucking that number I just read of a second. All right, so that's defined as a meter. So, however far light travels in this amount of time is considered a meter. All right, so speed equals distance divided by time. So the distance is equal to speed multiplied by the time or some shit like that. Well, anyways, it's just basically how far light travels in this amount of time. All right, and you get the distance. But like I said, the distance might have changed. I don't know how if the units, the SI, the standard units have changed, but so far, according to the book, that's what we're going with. All right. All right. So we're going to keep going. Mass is a measure of the amount of material of an object. A feather has a less mass than a baseball, which in turn has less mass than a cylinder block. The ideal standard for mass would be one that is like a standards of time and length based on something that is in the same throughout the universe. For example, the mass of a hydrogen atom, atom. Unfortunately, physics' present day ability to measure mass in the atomic scale is not yet precise enough to give a reality or give really satisfactory standards of mass for the time being. The kilogram, abbreviated kg, is defined to be as part mass of a special cylinder of a platinum iridium alloy kept in a repository near Paris, France. This standard of kilogram isn't very portable, and physicists look forward for one day when a kilogram is a fundamental SI unit. Oh, okay. And like I was saying, I think they already have that. I forgot how many atoms, or if it was the Avogadro number, they find out exactly how many atoms, but I believe they already solved this, but also I already solved this in my own units. I have my own units, guys, that we are going to go over. I just forgot to grab them out. But if we watch my old videos, you'll find the SI units that I have. But anyways, what it's saying is, here's a little piece of metal that's being kept hidden or protected. So that's exactly one. What is it? 1 kilogram or one whatever that I just said. This cylinder is defined as a mass of precisely 1 kilogram. There you go. This is 1 kilogram to ensure that the repeated measurement of its mass given in the same value, the cylinder has to be treated very carefully to prevent even a small number of atoms from being scraped off. So, like I said, it's being protected by a whole bunch of little jars on top of jars and a vacuum seal and shit. Crazy shit. All right. So, anyways, but I believe they already solved that. And like I said, I have my own units based on water because we're part of the reefing hobby and we fucking do everything based on water. But I believe they already solved that shit. If I'm correct, but like I said, none of that shit really fucking matters. I mean, it does matter, but you guys can go and fucking figure out the details yourself. All right. There's a watch out box right there that I think is very important for you to watch to hear. So let's read that shit. I think it's good enough. Anyways, watch out. Mass and weight are different quantities. It is important not to confuse mass and weight. While an object's mass tells you how much material an object contains, its weight tells you how much strongly gravity pulls on that mass material. Pulls on that object's material. Consider a person who weighs 110 pounds on Earth corresponds to a mass of 50 kilograms. Gravity is only about 1/6 the strength on the moon as it is on Earth. So the moon, this person would weigh only 1/6 of 110 pounds, or about 18 pounds. But that person's mass of 50 kilograms is the same on the moon. Wherever you go in the universe, you take all of your material along with you. We will explore the relationship between mass and weight in chapter 4. All right. All right. Units for many other physical quantities can be derived from the fundamental units of time, length, and mass. For example, speed is measured. What the fuck? Hold on, guys. Hold on. Man. Oh, now I know what happened. Sorry, guys. The shutter button. The thing I have to hold the shutter button. Kind of dislodged itself, and the shutter went down. Anyways. Units for many other physical quantities can be derived from the fundamental units of time, length, and mass. For example, speed is measured in meters per second, and weight is measured in kilogram times meters per second, or kilograms meters per second squared, kgm over second squared. Some derived quantities are used so frequently that physicists have named a new unit to represent them. For example, the SI unit of weight is the Newton, equal to 1 kilogram times mass per second squared, or about 0.225 pounds. So let's see what that's saying, because that's really important right there, actually. This is a we should probably get like a sheet and write all these shits down. Honestly, when we start converting, it would help a lot. So 1 kilogram and times meters per second squared. So that means that it's traveling. So or the amount of the amount of waybills that it's pushing. All right, so you got the mass and the amount of waybills that it's pushing, and that equals pounds. So weight. All right, so mass per second squared is an acceleration, and kilograms is a mass. All right, and it gives you 0.225 pounds. I'm just gonna put a LB. All right, for pounds. All right, but that conversion is really important because we're gonna be using a lot of conversion shits. Talking about that, I can already see the conversion units. Let's go. And talking about conversion units, it's right there. You see that? And like I said, guys, if you guys follow, you guys should be able to calculate how escape velocity, how fast you have to be going to escape the Earth's gravity and all that bullshit. All right, you should be able to do that shit on your own. And if you build a rocket or some shit fast enough, there's no reason why you can't escape Earth's gravity. All right. Anyway, let's keep going. In science and in ordinary life, a variety of other units are used for time, length, and mass as well. See, it's straightforward to convert between different units of the same quantity. In addition to second, some other common units of time include the following: 1 minute is equal to 60 seconds. 1 hour is equal to 3,600 seconds. 1 day equals 86,400 seconds. And some other units of length that are handy when discussing size and distance include discussing sizes and distance include millimeters, mm, centimeters, cm, and kilograms, km. The units of length are related to meters as follows. Oh, that's good. I can still read it in the book. Good shit. So 1 millimeter is equal to 0.001 meter. 1 centimeter is equal to 0.01 meters. 1 kilogram is equal to 1,000 meters. Yeah, 1 kilometer. 1 kilometer is equal to 1,000 meters. Although all right, although the English system includes inches, feet, and miles, and much older than the SI. Wait. Although the English system of inches, feet, and miles is much older than the SI today, in English systems actually based on the SI system, the inch is defined to be exactly 2.4 centimeters. A useful set of conversions is as follows. 1 inch is equal to 2.4 centimeters. 1 foot is equal to 0.3048 meters. 1 mile is equal to 1.609 kilometers. You'll find more conversion factors in Appendix A. We can use conversions such as these to convert many quantities from one set of units to another. For example, the Saturn V rocket used to send astronauts to the moon stood about 363 feet tall. However, we can convert the height in meters. How can we convert the height in meters? Figure 1 to 4 shows the technique. When doing unit conversions and or other multiplication and division variables, Units can be multiplied together, and they can also be canceled if the same unit appears in the numerator and denominator. From feet to meters, that Saturn rocket that is sent to the first human to the moon is 360 feet meters. How tall is that in meters? That's actually pretty easy to solve. I don't know if you want me to solve that for you guys. Say something. All right, but let's just do it. All right, no matter what, 363 feet. All right, so 1 foot. Oh shit, not 1 foot. I think it's 3.4 feet is equal to 1 meter. Some shit like that. I don't know. We'll figure it out right now. You guys figure that shit out. But let me know if we're going right. But we're going to have to solve it either way right now. Because look at this. We're having an even bigger problem to solve right there. Sorry, I'm not reading the text to myself. All right, let's go. This is the problem that we're doing right now. Oh, I know what's the problem is that shit's in the way. Hey, we're gonna come back to that. So this is my answer. If you're on the chat, could you or I was gonna say if you could do that calculation for me, 363 divided by 3.4. But let's just where's the calculator shit? $106.764 meters, but that's not the answer. So we got to do it a different way. So let's go right there. All right. If you see it, this is my old work in the past. You see that? This is when I did it by myself. All right. So this is what I did on my old work, but let's read what the book says and then we'll go over what I did. All right. All right. To convert units, for example, to convert the distance in feet. Oh, do you guys want me to zoom? Oh, let me get that shit out of the way real quick. And like I'm just doing the text. Like if you guys reading this shit for the first time and you guys don't know what to do, you're gonna be like, oh shit, I tried to do it and it didn't work out. You're always gonna feel like that you're not solving anything. You know what I mean? Hey, wait, I got 105. Wait, what was the answer that I said? Yeah, you know what? I'm fucking right. On my answer, I got 105. 10. Anyways, fuck it. Let's just let's I'm fucking right. But let's go with what the book says, all right? Let's go with what the book says. Hey, how many feet are in a meter? it's 3 feet plus 4 inches, right? Oh man, wait, it might have not even been 0.4. It would have probably been like point something because it's 6 inches. I mean, 12 inches. What's 12 divided by 4? So the real answer would have been 4 over 12 right there. Like it would have been 3 feet. 3 point. I would have put 3.4 over 12, and that would give you the exact. But anyways, let's read what the book says, and then we'll go over what I'm doing, because we're doing it kind of like a chemistry way, because we're not really a chemistry way, but well, yeah, the chemistry way. When I learned in chemistry, I just apply it here, and you should be able to do the same shit. Because why is it so blurry? All right, I think that's the best it's gonna go. So, anyways, to convert units, for example, to convert units, for example, to convert a distance in feet is a distance in meters multiplied by 1 in the appropriate form. Multiplying a number by 1 does not change the number. So 3. So let me get the notepad real quick, or could you guys see it? So what I was saying is 363 feet is equal to 363 feet times 1. Okay, not very fucking helpful. So, anyways, then it says 2. To find the appropriate form of 1, begin the conversion between the two units. So it says what right here? 1 foot is equal to 0.3048 meters. So if 1 foot over 0.3048 meters is equal to 1, and 0.3048 meters over 1 foot is equal to 1. So basically, they just reversed it. That's all they're doing right there. You see that? They just fucking went up and down. All right. And divide by one side to the other. So you divide a number by equal to the number, and result is always equal to 1. This gives two ways to express the conversion between in meters. So what the fuck does that mean? So let me do it for you in a little bit different way. Doing the same numbers they gave you, or they gave us. So it's, oh man, that looks. I'm not sure why my stylus doesn't work too well. Anyways. So given the numbers they give us, 3048, right, meters, and if you have it up over here, this equals 1. You see that? All right. So if I have an apple or some kind of fruit, see that, and another apple up here, that equals 1. You see that? That's all they're doing. Okay. So you see that? So it equals 1. Anyways, let's keep going. There you go. All right. So if you try multiplying 363 feet by the first form of 1, 363 feet is equal to 363 feet times equals 1 equals 363 feet times 1 foot over 0.3048 meters is equal to 1,192 feet squared meters. And it's saying this is wrong. You see that with an X? So it's saying that shit's wrong. All right. Don't really follow what the fuck they're saying in the book, guys. I'm gonna show you guys the real way to solve this shit, so you always get it right. If you just fucking do the right steps. Anyways, if instead you multiply three, so this is the correct approach. It says the correct approach. If you instead multiply 363 feet by the second form of 1, 363 feet equals 363 feet times 1 equals 363 feet. What the fuck? Is equal to 0.3048 meters over 1 foot equals 101 meters. Okay. God. Okay, let me show you guys what the fuck they're doing. Okay, so if you look up here, right? Am I pointing it to the right spot? Okay. You see, if you up here, you see these two forms of 1 that they have? All they did was grab 363 3. Let me do it on the notepad also at the same time. All right, so you know how they have 363? All right, and they have option 1 and option 2. All right, and here's let's say this is option 1, and to the right, this is option 2, and all they're doing is multiplying by both of them, and one of the answers is going to be correct, and that's all they're doing. But you guys don't even pay attention to that bullshit. I'm gonna show you guys how to really solve the problem. All right. All right, so here's more of where I would do, but let's go back to when I was doing my shit. I'm gonna show you guys what I'm doing over here. Hey, El Benny de Cali, bro. What's up, G? Thank you for joining, bro. We're learning physics today, bro. Cause it's university, bro. Cause I'm gonna treat my channel as a university. You know what I mean? We're gonna fucking fuck all that shit up. All right, so that's my work when I was in university. That's my work right there. So why did I put 47? What problem am I doing? Oh fuck. uh Hey guys, scratch that shit. Okay. Let me show you guys something real quick. Let me show you guys how to really solve this problem in an easier way. All right. So whenever this is I'm gonna give the credit to Miss Shin. She's the one at Lee High School in South San Jose. All right, she's the one that taught me this. So you get 363, right? Feet. All right. And then do like a little fence. And what you want to do is transfer the feet to this side. So feet. And the desired amount is up here in meters, right? Okay. So if you look at the two options right here, the one that's in foot in the bottom, you see where it says 1 foot? All right. So 1 foot is equal to 0.3048 meters. All right. Equals, and the way you do this shit is you just multiply 363 by that number, and then whatever number you get right there, you put it right here, and whatever you have in the bottom, you divide it by the number that's right here. All right. And when you do that, you're going to get 101 meters. Okay. But let's go to a even more harder problem that's right here. That's the problem that's up here that I did over here. Oh shit. All right, the problem that's up here is the problem that's down here. So let's read the problem and then let's do it together. All right. I had a 3.8 GPA when I was attending the university. Oh shit, at Benny the Cali for reals, bro. Damn, bro. Hey, what were you studying, bro? Let me know. I definitely want to know what you were studying for sure. I totally understand where you're going into stuff like this. I can totally understand going into stuff like this. Oh shit, that's cool. That's what's up, bro. Hey, bro, thank you for joining, though, man. Maybe I gotta fix the white balance on my camera. Oh, well, fuck it. Anyway, so let's read the problem if we can. So, anyways, it says the white throat, needle litier, horrendous, puptis, some shit, something cactus can travel at the speed of 47 meters per second in level flight. Falcons can go even faster if they dive to do so. What is the speed in kilometers per hour? And what is kilometers an hour in miles an hour? All right. So what it's saying is what the kilometers an hour into miles an hour. Wait. Oh, so it's asking two questions right here. So it's saying if a falcon, basically this is the name of a falcon travels at 47 meters per second in level flight. So always when you read a physics problem, guys, let me see if I get close, a lot closer. All right, there's a problem right there. Is this physics 12? Hey bro, this is a university level physics, bro, and we're on chapter 1. So if you're learning physics for your school, definitely tag along. Hey, but I'm not sure if you have a wrench, bro, but let me drop you a wrench. But yeah, we're definitely learning physics right here. Where's my live? Right. Let me see my live. I'm not sure how to find my own shit when I'm on live. But yeah, we're learning physics right here, and right now we're gonna do conversions between 47 meters per second into kilometers per hour and in miles an hour. All right, so this should be pretty easy. Why isn't it going? Anyways, fuck it. Hold on, let me grab my other phone, guys, real quick. Where's my other phone? Oh, I think it's charging. Hold on, real quick. But let me bring out the notepad so you guys could see what we're gonna do right now. All right, there you go. And if you guys have any questions, any physics questions, definitely drop them down. Hopefully they relate to the book. If they're like more advanced physics where it's later on in the book, I'll probably just answer that shit when we're on that chapter. When we're on that chapter. But this is physics for people that don't know any physics, and I'm gonna do all the work, and you guys don't have to do anything. And if you have any questions, always drop it down. But also, we're doing the chemistry series, so we're on chapter 3 on chemistry, and right here on physics, we're on chapter 1. But I'm trying to go on my live real quick, see how trying to see who has a wrench or not. Oh, let's see. Because sometimes when I work with water, I usually delete people. All right, Stephen Yang, Kang, drop another comment, bro, and you should have a wrench. Thank you for joining, bro. All right, so let's write down what we do got. So you see how it says 47 meters per second. All right, let's write that down. So we have 47 meters and then per second, right? All right, so oh shit. You guys don't see what I'm doing. Hold on. All right, so we got 47 meters per second, right? All right, so this is called the picket fence form. Do this method and you'll sorry, I thought I heard some dogs outside. So do this method and you'll never get anything wrong. All right, so I'm gonna go this way, and then the equation's gonna continue going this way. All right, I just don't have enough space. Or let me see if I could change the pixels on this. Oh, but you guys can't see that shit. Okay, I'm gonna work with that. All right, so we got 47 meters. Oh wait, I'm gonna put 3 sig figs, or right, or one decimal right there. All right, meters per second. All right. So do this method and you'll never get anything wrong, really. So this is called the picket fence form. All right, there's a different title to it. I forgot what it's called, the more accurate title, but this was Miss Shin from San Jose State. I mean, from Lee High School. She's the one that taught me this, but and the university they didn't really teach me this, but do this method and you'll never get it wrong. So whatever's on this side up here, always bring it to this side. All right. And then whatever we get up here, bring it to this side. Okay. And whatever we get up here, bring it to this side. So okay. So just remember this diagonal form, okay? All right. So this is called the picket fence form. So we're trying to get to, what is it? Minutes per hour or some shit. I forgot what the fuck. Oh, in kilometers per hour and in miles an hour. Okay, so 169. Huh. Okay. All right. So let's just keep going. All right. So we got meters up here. So and I need a meters down here, and I'm trying to get to kilometers. All right. So kilometers, km. Okay. So 1,000 meters is equal to 1 kilometer. You see that? And remember, in the diagonal form, like I said, I need kilometers now over here, and I'm trying to get to 2 miles. Okay. So I'm a and remember again, guys, I'm not a teacher or anything. This is my first time doing this shit, but don't worry. All right, so oh yeah, so 1 kilometer. All right, so so now we got to convert kilometers to miles. All right, so 1.609 kilometers is equal to 1 mile. Okay, you see that? And then I'm in. If you look at the original problem, they want us to get to, what is it? Miles an hour. All right. Oh wait. Yeah, one of them is miles an hour. So let's do that shit. and the other one's in kilometers an hour. Okay, I know what I'm doing. I did both of them at the same time when I was solving that shit. All right, let's keep going. We got to calculate the velocity of the projectile traveling southwest with 45-kilometer winds pushing from the northeast. Oh, Benny, we're gonna solve all those, bro, for sure. Laughing my ass off. Just kidding. Hey, no, but for reals, bro, we're gonna solve those for sure, Benny. I forgot what chapter it is. I think it's chapter 4. Or we're gonna solve that though for sure. Equations like that, even if you made it up, bro, we are gonna solve that, and we're gonna solve the degrees because we have to solve because he says it's northeast. Then you have to put the degrees, so you got to say, oh, it pushed 30 degrees northeast or north of east, or you could say east of north depending on the direction. Once we get to vectors, there you go. Once we're at vectors, we're gonna solve all that shit, which is not that far. All right. So anyway, let's keep going. So when I was doing this, I'm just gonna keep going. All right. So we're at miles now. Okay. So now, but you see, we're at seconds over here. Seconds. Whatever I do up here, I'm gonna do up here. All right. This is gonna be really confusing until we practice. Okay. All right. So we're at seconds. So this is done in terms of converting mass. All right. This is mass right here. So now what we want to do is focus on seconds and convert seconds into hours. Okay. Seconds into hours. But we already converted the masses that we wanted. Okay. So now we got to convert the seconds. So this is equal to 1 second. All right. Yeah, to 1 second. Okay. And then like I said, following this, let's say I draw another arrow. So following that, following that 60 seconds is equal to 1 minute. You see that? And you see how the seconds will cancel up here? See diagonal, but the equation, I can't fit it all, but let me show you what's happening. All right. So then you got seconds, right? So yeah, 60 seconds equals 1 minute, right? And then 60 minutes, because remember, we got to just travel over here and you always get it. And then 60 minutes is equal to 1 hour. And guys, I'm reviewing myself as I go along with you. But since I've already done this before, it's gonna seem like I know my shit, but it's me also remembering at the same time. All right, so now minutes, you see how they're always canceling, and then the seconds will cancel. That's how I know I'm doing it right. Okay. All right, so then I'm at 60 minutes. Is equal to 1 hour. All right, and then that would equal. All right, so I on my book, I'm just going with what my book says or what I did in my book. Let me show you. All right, you see my book? I just wrote the answer. All right. And then the answer I wrote, what looks better? I don't know. Okay, the answer I wrote was 105.158 something, and then it says 4835 on the calculator. Okay. All right, you see that? But how do I solve that using what I was just doing? Okay, so let's go back to my chingadera. We're gonna figure out where I got this, or what does that mean? Okay, so what I'm gonna do is, you see all the top numbers, all the numbers on top, I'm gonna multiplying with each other, and then all the numbers in the bottom, I'm gonna multiply them with each other. So what does that mean? Okay, so I got 47 times 1 times 1 times 60 times 60. Okay. All right. So let's draw that shit out. So 47 times what? Times 1. Wait. Fuck that, times 1. So 47 times 1 times 60 times another 60 equals a number. And then the bottom half, which is what is it? 1 times 1,000 times 1,000 times 1.609. Damn, that's hella huge. Hold on. 1.609 times 1. Hold on, let me see. Times 1 times 1. All right, times 1 times 1. Hold on, let me clear that out so you guys can see what's going on. All right, there you go. Equals a number. Oh shit. It equals a number in the bottom, right? All right, so do those numbers. We're going to multiply them in the calculator together. It's been years since I last did this type of work. Hell yeah, Benny. We're going to review, bro. So if you did this work before, bro, we're going to review, bro. Because with this, bro, we're going to start building our own technology with the Raza. Because we are our own people. Even though we're landless, bro, we're going to fucking build technology and all that shit, bro, and get us out of poverty and all that shit, bro. I'm working on a kind of a video that I'm using off of like a different. I don't know. I'm working on some shit right now, but bro, this is what our people really need for sure. And I'm glad you know this shit. Physics was tight. I struggled with calculus like bad. Hey, bro, for calculus, I only studied for a week, bro, and I still managed. Like, I mean, I only studied like 7 days throughout the semester, and I managed to pull off like a C, the C plus. I'm like, fuck it, I passed. That's all I needed. But if I would have had like the resources, bro, like an actual book, and dude, it was a disaster, bro. I was basically almost like living in the streets trying to go to school, bro. Fuck all that shit, bro. I mean, it's tough as fuck. But anyways, going back to this shit, but going back to this, we're gonna multiply all the top numbers and all the bottom numbers of right here, what we did earlier. So remember, right, what we did is get the meters to kilometers, kilometers to miles, and then seconds to minutes, minutes to hours. You see that? And then we multiplied all the top numbers together and all the bottom numbers together, and we're at right there. Okay, so let's go get the calculator. So it's 47. I'm not sure why that's just like that, but 47 times, what was it, 60? Let's go look. Yeah. Oh, wait. So you guys don't think I'm fucking with you guys. Times 1 times 60 times, oh shit, times 60 times, that's it, is equal to 169,200. 169,200. All right, and then we're gonna multiply all the bottom numbers. One times 1,000 times, was it 1 point? This is, don't forget that fucking period or that dot. 609 equals 1609. All right. So now we're gonna take the top number from this equation right there. See all these numbers multiplied together. Oh, and then we're gonna divide it by all the bottom numbers multiplied together. Okay. And that gives us 169. Damn, that looks ugly as fuck, but my stylus ain't working too well, guys. How that shit ain't working. Hold on. We got 169 200 divided by 1609, right? Equals, now we got to figure that one out. Was it 1609? Oh shit. 169,200 divided by 1609. If I fuck it up, let me know, guys. Is equal to 105 158. All right. I forgot what the fucking units were. We ended up in, I guess we, anyways, fuck it. Fuck it. But that's the answer. 105, 108. So let's go look at the book. Wait, and let's pull up our 105, 158 or whatever. But then look over here. They just rounded it out to 105. Okay. There you go. See that? And that's all. That's how you basically solve it, all these problems. And remember, even though we're not really gonna do a lot of problems, we're just gonna go like one or two examples following the book. That shit's really important. But like I said, you could do it the way the book does it, but it's kind of very similar. It says, watch out, use a correct conversion factor. Yeah, see, right there, what they did wrong is they had to put the kilometers in the bottom and the miles on top. But right here, you see right here, they're trying to go from kilometers to miles. Anyways, do it. You guys got to practice that shit. That's all I got to say. But even though I know I kind of make it look like easy, and at the same time, like I don't know what the fuck I'm doing because I am reviewing. That's how you solve that. You see that? So just do this fence form. Watch. Just do this fence form. Kilometers. I mean miles to kilometers. But you see these numbers in between, like the 1,000 and the 106 something. Those numbers are basically standards. Look, those are conversion standards that you gotta have like a different paper. That's where I got those. You see that? It's not that I fucking memorized them. I was just looking at the problems that they give you. Maybe I should have showed you that part, but see the conversions right there. I didn't even do it the way they did it. That's some funny ass shit. They did 1 hour to 36 some shit seconds. Fuck. There's different ways to solve it, guys, but as long as you get the same fucking answer, okay? Uh what they did, so let's just put a hypothetical out there. What they did, so let's say we're at, I forgot whatever the fuck per second, right? What they did is they grabbed 360 some shit. Oh wait, let me write that nice. Seconds is equal to 1 hour. You see that? I probably did it the longer way. I did from 1 second. I went to what was it? 60 seconds. Oh shit. I went 60 seconds is equal to 1 hour. Oh shit. Oh shit. No wonder I'm doing this wrong. I corrected myself. All right, I did 60 seconds is equal to 1 hour. You see that? I mean 60 seconds. What the fuck am I saying? 60 seconds is equal to 1 minute. And 60 minutes is equal to 1 hour. All right. And then if you multiply these two together, it should equal, I'm not sure, but it should equal 363. All right. In physics, there's so many times, there's so many more than one way to skin a cat. Yeah, see? So Benny knows what I'm talking about. But that's the difference. The way the book did it, they just went from straight from seconds to the hour. You see that? I probably did it like I said, a way shit that I know off the top of my head. Who the fuck would ever fucking know unless you're like one of those pendejos that memorizes shit? Who the fuck would know 3,600 seconds is in 1 fucking hour? I mean, realistically, you know what I mean? But if you have that cheat, like how we have it right here in the book, right there, fucking use it. You know what I mean? But that's the difference. The way I'm solving it, I just went with the shit I know. I know 60 seconds. I mean, what 60 seconds is equal to 1 minute, and 60 minutes is equal to 1 hour. You know what I mean? So that's just the way I was doing it. But I like to show you the way the book does it, so that way you guys be like, oh, Henry doesn't fucking show us what the book says, and he does some weird shit, and I don't know what the fuck's going on, and all that bullshit. But I'm just showing you what's up. And man, and Benny the Cali's fucking MVP right here because he knows physics and shit. And oh wait, we already did that shit. And then you can even ask Benny the difference between the physicists and the or physics and chemistry, or those types, like physics, chemistry, and biology. The mathematicians is that we need energy and matter. Otherwise, we wouldn't have a job. All right. So quantity versus units. In this book, we'll often use symbols to denote the values of physical quantities. We always write we always write these symbols using italics. Some examples include symbols V for speed, B for magnetic field, and E for energy. As these examples show, the symbol, hold on. The symbol is not always the first letter or the name of the quantity. By contrast, the letter that we use to denote units such as meters, M for meters, S for seconds, and kilograms, kg are not italicized. If the unit is named for the person or the letter is capitalized, an example of this unit is power, the watt, abbreviated W, named with the Scottish inventor James Watt. In some cases, the symbol is used in more than one quantity. For example, uh, for example, hold on, is hold on. In some cases, the symbol is used for more quantity. One example is sketch rope. The letter T is not italicized and is used an abbreviation for the unit. Sorry, guys, if I missed a sentence, you guys at least got it on the screen. You'll often need to pay careful attention to the context in which the symbol is used to discern the quantity or the unit represents. I don't know who gives a fuck, but none of that shit was really important. But all they're saying is sometimes just because of the name, it doesn't always have the right chingadera. And then right here, this is some really important shit actually right there. I don't know how to tell you guys this. This is kind of like using the metric system. So if you know how back then they used to talk about kilobytes on the computer, and then they came out with megabytes, and then they came out with gigabytes, and now how we're at terabytes. Eventually, there's gonna be a petabyte. I mean, judging by what's going on, right? There's gonna be once we pass terabytes, we're gonna be at the pentabyte, and then we're gonna be at the exabyte, and then at the zettabyte, and then at the yottatabyte, some shit like that. And then if we go the other way, this is going bigger. And then if you go smaller, you go the other way from kilograms. You go to a hecto, deca, decimeter, centimeter, millimeter, macrometer, nanometer, picometer, or pitometer. That's why some people say nano tanks, and then some people say pico tanks. And then you got fetmometer, and then a ottometer, a zeptometer, yoctometer, some shit like that. Anyways, I think I said that shit right. I don't know who the fuck, but all that shit is just multiplied by 10 or 100 or some shit, guys, and that's all you gotta fucking know. Just add an extra zero to that shit. Scientific notation. All right. Physicists investigate objects that vary in size from the largest structures in the universe, including galaxies, clusters of galaxies, down to the atomic nuclei and the particles found within nuclei. The time intervals that they analyze range from the age of the universe. Age of the universe to a tiny fraction of a second. To describe such a wide range of phenomena, we need to equally wide range of both the large and the small numbers. To avoid such confusing terms as a million, billion, billion, physicists use a large number are consolidated into the term consisting of 10 following many zeros. What the fuck? Many zeros that standard the shorthand system called scientific notation. All the cumbersome or some shit zeros that by an exponent, which is written of a subscript. The exponent indicates how. Sorry, I'm reading sideways. Sorry. Also tells you how many must be multiplied together given the desired number, which is the exponent is also called the power of 10. For example, 10,000 can be written as 10 to the fourth or 10 to the fourth power, because 10 to the fourth, 10 times 10 times 10 times 10 is equal to 10,000. Some powers of 10 are also common that we have created abbreviations for them that appear as a prefix to the actual unit. For example, the prefix and its abbreviation is for several common powers of 10. We're on the second page, guys. But oh yeah, you guys could read that shit too. But you guys could read it better than me. I should just read it off the computer. I probably could read it better off the computer than trying to read it off the book. Laughing my ass off. They're gonna be like Henry on the mean one, laughing my ass off. There are the clues in the letters. Yeah, see. So basically, all I read, all that shit said was basically everything goes by 10 and everything what we're talking about. You know what I mean? But none of that shit really matters. What matters is up here. And what they were talking about, uh, to write any number. So if you see like 3600, all right, the decimals over here, you go 1, 2, 3. So you would just put 3.6 times 10 to the fucking third. And that equals the same shit. All right. That's all this fucking thing. Right? Right, Benny? 1, 2, 3. Yeah. That's all we just read. And each one of those exponents has a name, and the names are right there. But you really don't need to remember that shit. But as you keep doing physics and chemistry, those numbers, you're gonna be doing them so often that you just kind of remember what they are. And those are conversion factors also. All right, guys. Yeah, Benny said it's all good. That equation's good. That's right. So he said that that's the right answer right there. See, like people put Raza down, but Raza has a lot of smart motherfuckers, man. You know what I mean? And that's what I mean. That's why it's our time to shine. And because of all the Raza podcasting, or the podcasts are started in California, the way our people are, it's spilling into all these YouTube channels, and now it's like all the cyberspace fuckers. They're gonna have to be held accountable. You know what I mean? Because that's just the way Raza rolls, and Raza, we don't, you know what I mean? We're all different, and it's spilled into YouTube and all that shit, and there's leaders in the community, and like right here we got Benny, even though he doesn't do content. Hey Benny, I don't know if you do content, but we all know Benny of the Cali. He's one of the leaders in the community also. You know what I mean? But anyways, let's just keep talking, guys. I mean, let's keep reading and all that. And if you have any questions, let me know. And like I said, we're gonna be doing this in the book. I mean, the problems in the book, we're gonna be doing them and all that shit. 1.5 centimeters. Sorry, I'm reading the next problem real quick. Oh, I'm reading the next problem. All right, so we're right here. I was wondering where we're at. I forgot I flipped the page. All right, the scientific notation numbers are usually written as a figure between 1 and 10, multiplied by the appropriate power of 10. The appropriate distance between Earth and the Sun, for example, can be written in 1.5 times 10 to the 8 kilometers. That is far more convenient than writing 1,500, 150 million kilometers, or 150. Oh yeah, they even set it out for us. 150 million kilometers, a power output of 2.5, 50 watts to 250 watts can be written scientific notation as 2.5 times 10 to the 3 watts. Alternatively, we can write this as 2.4 kilowatts, where 1 kilowatt equals 10 to the 3 watts. Note that most electronic calculations can be shorthand for scientific notation. To enter the number 1.5 times 10 to the 8, you first enter 1.5 and then press the key labeled as exponent EE or 10 to the X, then enter the exponent 8. The key takes care of the X to the 10th part of the expression. The number will then appear in your calculator display as 1.5 E8 or 1.58 or some of the variation of these. Typical, the x to the 10 is not displayed in such. There are some variations from one calculator to another. You should be able to spend a few minutes to make sure you know the correct procedure for working with numbers in scientific notation. You will be using the scientific notation in your study to physics, in your study of physics. So this is the time we spent. Watch out. All right. And then it says this watch out box. I think right here, depending on your calculator, it might give us you might want to take your calculator out if you have one. But let's see. Let's see what it says out. Watch out. If you know your calculator expression, scientific notation, confusion can result from the way your calculator displays scientific notation, since 1.5 times 10 to the 8 is displayed as 1.58 or 1.5 e to the 8. It is not uncommon to think 1.5 times 10 to the 10 to the 8th is the same as 1.5 to the 8th, and that is not correct. Hold on, let me read this real quick, see if it's really important. 5 times is even close to 1,000. Some shit coming to right at 1.8 if you include the decimal, perhaps. Okay, hold on, guys. I don't think that shit's really important. It's just basically saying know how the fuck your calculator displays shit. You know what I mean? We can figure out the rate of cheese melting on a tortilla at the rate of 225 degrees Celsius for the perfect melt. Laughing my ass off. Tengo hambre. Oh yeah, make sure you guys check out the food series that we have going also for the shorts. It's only on the shorts. We're not gonna do that for the lives or the main videos. But anyways, basically the watch out just says know your calculators bullshit. All right, you can use scientific notation for numbers that use less than one by using a minus sign in front of the exponent. Oh, you can use scientific notation numbers for less than 1 by using a minus sign in front of the exponent. A negative exponent tells you to divide by the appropriate number of tens. For example, 10 to the minus 2 means to divide by 10 twice. So 10 to the minus 2 is equal to 1 over 10 times 1 over 10 is equal to 1 over 100 is equal to 1 over or is equal to 0.01. Table 1.2 also includes negative powers of 10. You can also use scientific notation to express a number such as 0.00245 sorry guys, 0.000245 is equal to 2.45 times 0.001 is equal to 2.45 times 10 to negative 3. Basically different ways to say the same shit. Again, the standard for scientific notation is the first figure is a number between 1 to 10. This notation is particularly useful when dealing with very small numbers. A good example is the denominator of a hydrogen atom, which is so much convenient to state in scientific notation 1.1 times 10 to the minus 10 meters as a decimal, 0.00000, a whole bunch of zeros, 1 meters, or a fraction of 110 trillionths of a meter. All right, fuck all that shit. It's basically saying know your decimals and all that bullshit, guys. Let me see what it says right there. Got the concept. Basically, here's a whole bunch of conversion factors, guys. All right. Anyways, fuck all that bullshit. All right. So here's a problem that we have. So let me get the sketchbook. All right, there you go. The hair on a typical person head grows at an average rate of 1.5 centimeters per month. So let's write that shit down. What did that say? What did it say? What did I say? 1.5 1.5 centimeters per month. You see that? 1 month. Okay. And no matter what it's asking me, I can already tell you what I'm gonna be doing. Watch. I'm gonna be doing the little fence shit. Watch. Right here is gonna be a centimeter and whatever unit they want me to keep going. All right. So approximately how far? Oh, let me. Well, hold on. There you go. Approximately how far in meters will the end of your hair move during a 50-minute physics class? Express the answer using scientific notation. Ah, motherfuckers, dude. They really want to fuck us over. All right. Let's pull out the fucking sketchbook. How far in meters? All right. So they want us to go in meters. All right. So centimeters. So remember 1,000 centimeters is equal to 1 meter. Because they want us to say how far in meters. So we want to find out how many meters does the hair grow. There you go. How far in meters does the hair grow in 50 minutes? So time. Okay, so that's basically the problem they're asking, right? So 1,000 centimeters. So remember, I went from right here to here to now I'm at meters, which is the answer they want, right? So that will solve my meter problem, right? That will solve my meter problem, which it wasn't that much of a hassle. But now we got this shit. The month is gonna fucking kill us because they want us in minutes. At least they didn't say seconds. Otherwise, fuck it. All right, so 1 month. So this is gonna suck. All right, so month has to go up here and then go down here. All right, so let's give it a try. Let's give it a try. All right, so 1 month is what I'm just gonna put I can't put just M because people are gonna think meters. All right, so 1 month is equal to how many days is a month? On my book I put 30 days. All right, so 1 month is 30 days, right? Right, and then 30 days. 30 days. So now I'm over here at days. So from days, I could go I could go 1 day. So now we go 1 day, right? That will cancel the days, right? So 1 day is equal to 24 hours, right? And then from hours, I got to put hours up here. And then 1 hour, see that? See how the hours cancel? 1 hour is equal to 60 minutes, which is the time frame. I mean, which is the unit they want. They want it in minutes. If they want it in seconds, you just do another step. 1 minute is equal to 60 seconds, but they don't want it in seconds. They want it in minutes. So we stop. All right. And that equals, and then again, guys, all the numbers at the top, all right, they multiply together. And that's an easy one. So 1.5 times 1 times 1 times 1 times 1 is equal to 1.5. So I'm going to put 1.5. Oh, wait, let me put it over here. Fuck it. I already wrote that though. Fuck it. I'm going to put 1.5, right? Times 1. Wait, oh shit. Times 1 times 1,000 times 30 times 40 times 60. Okay. So let's put 1 times 1,000 times 30 times 40. Oh shit. Times 24 times 60 equals. We got to figure that out. So let's figure it out. So remember, that's my first problem right there. All right. So this thought came to mind, bro. Let's see what you got, bro. Never mind. I was gonna go in a rabbit hole about a educational topic. Hey, bro, do it, bro, for reals. Why not use 31 days? Because every month has 31 days in it, unless it's a February leap year and y'all messed up, homie. You messed up. You messed the homie up. Oh yeah, Benny. Plug in whatever number is there. So we'll put that instead of 30 right here. We'll put 31. Or what number did he say? 31 days. We'll put 31 also. Okay, so we'll get two numbers. Okay. So let's get those two numbers. Oh man. I'm gonna switch this up. I'm gonna multiply the 31 last, so we get the second number easy, so you can know, so you can see what I'm telling you right now. All right, so let's pull it up. Let's pull up the calculator. Sorry. So 1 times 1,000 times. I'm gonna skip the 31 for now. You'll see why right now. Times 24 times 60. All right. So and then times. I put 30. All right, and I got that number. Well, what is it? 43,200,000. Fuck. All right. What was the number? Oh, sorry. Wrong number. 43. 43,200,000. I believe that's the number. All right, and then let's put 31 because Benny said 31. How do you go back? I mean, how do you delete 31? You get 4 640. All right. All right. See? So we got our two numbers right here. Let me erase something real quick. Oh shit, what the fuck? All right. So these are the two numbers I want to divide. So let me go to the next frame. Oh shit. There you go. There you go. So now I'm gonna go to the next frame. So I'm gonna get this number divided by this number. Okay. So 1.5. Oh wait, guys. I fucked up. I fucked up. I noticed I just fucked up on something. Okay. On this one, I still have to keep going. Why? I'll tell you guys right now why. All right. So the answer right there would be that's the rate. What the fuck? Okay, that's the rate this is the rate at which the hair grows, but the question it's asking me, you see, how fast is it growing in 50 minutes? So what we got to do is multiply this by 50. Okay, so 50 minutes. You see that? So all we had to do was now it kind of changed the equation a little bit, but not really. So over here, this stays the same. The only thing that's different is 1.5 times 50. We'll figure that out. Okay. But either way, our equation is still the same. So what's 1.5 times 50? Let's figure that out real quick. It's 75. Okay. Bam. So imagine it's 75. Okay. Okay. So you guys could know what's going on. So it's basically 75. Yeah, fuck it. Let's leave it there. 75 divided by this number right there. Okay. And use either one. So we're going to use both of them and see what we get. So 75 divided by 43,200. Okay. There you go. This is the number I got. 1.7. What was it? 1.76 times 10 to the what? E to the 6. Wait. Oh, now I know why okay, so now I know what the minus said on the calculator when they said watch out. E to the minus 6. Yeah, that's right. That's right. That's right. That's right. I think I got it has to be a minus because it's going small, or it's a small ass number, right? Wait, no. Hey, bro, how do you read that shit in the calculator, bro? Uh, E to the minus 6. I think that's what they were talking about in the calculator. So I'm just gonna write E minus 6, whatever the fuck that means, right? I think it means 10 to the minus 6 or 10 to the 6. I'm not sure if that's a plus or a minus. All right, guys, this one right here. All right. All right. So that's using the first number that I got right here. So now let's try the 75 divided by the number in the bottom. Cause Benny said to use that number. So let's use that number. So 75 divided by 44 640 and then 0.000. There you go. Equals 1.68 0.680 times 10 to the, I'm not sure if it's minus 6, but it says e to the minus 6 on the calculator. Okay, guys, whatever the fuck that means, right? But now let's go back to the original problem. You see how they only gave us one significant figure right here? You see it's only one sig fig. Oh, let's say two sig figs. Fuck it. You see that? On this final answer, it's so back to Benny's Benny. So this is the answer I got, right? And then this is the answer Benny got using Benny's number of 31 days. So this is 30 days and this is 31 days, okay? But if you see these numbers right here, you see that? We got to take the average or the most average or the nearest whole number of certainty, the number that we actually know is fucking real. Um, over here is uncertain on the scale. We don't. This is not really for sure, but this is more. This is more theoretical. While in contrast, this is actual. All right. All right. So anyway, so what the fuck does that mean? So we went around to the nearest whole number. You see how the nearest whole number is actually the 7, because when it's 5, we round up, and when it's below 5, let's say it's 4, we round down. Okay. So if we round the top number, we'll get 1.7 times 10. Yeah, that is right. 10 to the minus 6, right? 10 to the minus 6. All right. So I'm getting confused of this E though. All right. So anyways, on the next one, on the 31 days, you see we get 1 point, but you see how this is above 5? This number right here, that's 6. It's above 5. So, oh, actually, don't look at that number. This number right here, this decimal point, look at the number right here next to it. So, from the 7, we looked at the 3. From the 6, we look at the 8 right there, right? So if we round up using that thing that I was telling you about earlier, we get 1.7 also. See that? Times 10 to the minus 6. All right. So if we clear this up, we get the same answer no matter what. You see that? So it doesn't matter if we say 30 days or 31 days, the amount that it's growing, it's so fucking small, it doesn't even fucking matter. You see that? Because the other numbers that were on this side, we did not really know. Those were uncertain of the scale. Let's say my scale that I'm using is too rusty from measuring all the fucking salt. You know what I mean? This decimal point might be all fucked up on my scale. You know what I mean? So, but either way, it really wouldn't matter at such small numbers like right here. It wouldn't really matter the amount of growth in 50 minutes. You know what I mean? But there you go. So now we're done with that problem. And I hope I make sense when I'm showing you guys the way I do. Oh, see, here's a problem right there. See, when I did it, it's the same problem that we just did right now. It's right there. See that? Let me see what did I use on. Let me pull out the other frame real quick. Let's see. Let's compare real quick. Da, da, da. I got a big old. I guess when I did it on my calculator, the number I got was 0.0001234. 1, 2, 3, 4. Yeah, 417,361. All right, on the calculator. You see that? And then I had to convert it. And I got 10 to the minus 5 though on my shit. You see what I mean? Yeah, see, when I did it on my calculator, I got 10 to the minus 5. But when I did it on this phone calculator, I got some other shit. That's why I said the book says to learn how to read your shit. And then when I look over here, it says 1.7 10 to the minus 5 also. I think I fucked up somewhere on the minus E, but like I said, I don't know what the fuck that E meant, but either way, we got the fucking answer though. Fuck it. But I'm just noticing on my calculation, I got unless and wait, hold on, let me count this shit. Unless I wrote it down when I was doing it. 1, 2, 3, 4, 5. Yeah, see, 10 to the minus 5. Benny says you need to use a scientific calculator, bro. Hey, bro, you're right, bro. I left. Oh, let me see if I have my calculator, bro. And you're right, bro. That's why you should be using a scientific calculator because está cabrón, está cabrón. Let me check my backpack real quick. But Benny's absolutely right. I should be using a scientific calculator, not just But that's why I was just multiplying regular numbers to at least get the main number right. I think it's because I need to write the scientific expression different on this calculator. All right, hold up. Let me grab my scientific calculator if I have it real quick. All right, hold on. Let me put my phone on mute real quick because that shit's getting annoying. All right, there you go. Yeah, bro, I definitely need a scientific calculator for sure. That's why the decimals are not adding up. But I know when I did it on the book, that answer is right for sure. Cuz it's matching when I did it on my calculator, it's matching the book, but when I did it right now with you guys, the phone's calculator is fucking I was going to say one of those words, but it's fucking whack. We'll say that. I was gonna say the other word. Oh man, where we grow up, baby. All right, let's go, baby. Let's go. So, anyways, continuing. I wonder if I could just move this right here. All right. Correct use of significant figures helps keep track of uncertainties in numerical values. Although physicists strive to make their measurements as precise as possible, the unavailable fact is that there is always some uncertainty in every measurement. See, that's exactly what we were talking about earlier. Remember the decimal points? That's why I only went with 2. Over here, I wrote a lot of decimal points after the 7, but those don't really matter. All right. This is not a result of sloppiness or the lack of care in the part of the person doing the measurement. Rather, it is due to fundamental limitations of how well measurements can be carried out. If you try to measure the size of a thumbnail using a ruler within markings in millimeters, a little judgment, you might be able to tell the length of very nearly halfway between those 2 markings on the ruler. You might be able to say that the length is approximately 15.5 millimeters. However, armed only with your ruler, it would impossible to say whether the length was 15.47 millimeters or 15.51 millimeters. If I missed a sentence, you guys got it right there on the screen. Except I'm reading sideways. 15.44 or 15.54 millimeters, we would say that the fourth digit is not significant. That is, it does not contain a meaningful information. Hence, this measurement is only three significant figures. We specify this implicitly by giving the measured values as 15.5 millimeters, by which means that it is between 15.4 and 15.6 millimeters. Before more precise measurements have more significant figures. Less precise measurements have fewer significant figures. So what the fuck does that mean? I'll tell you right now. Let me read the next sentence. Or hold. Let's just say it right now. Let's just do it. All right, let's go. What the hell they're talking about is from 15. Oh, fuck it. What was the number they're using? 15.54. All right. What it's saying is this number is the one that's uncertain. And from right here, we only got these three that we could actually measure on a scale or whatever instrument we're using. So what it's saying is there's only three numbers that really fucking matter. That's all it's saying. All right. So let's keep going. Oh, three numbers. And the only ones that matter after the decimal point is this one right here. The next one is one we use to round off. So that's why on our previous example over here, right here, we got 1.07 no matter what. I mean 1.7 no matter what. Okay. That's all it's really saying. All right. So let's read the last sentence and let's see what's up. All right, let's see. All right. An alternative way to represent the number would be to give the length of your thumbnail as 15.5 plus or minus 0.1 meters, which is a number after the plus or minus representing the uncertainty. All right. So all that it is saying back to over here, if we get that same number, that 15.54, what it's saying is this number right here. Oh, wait. This number right here is off. Wait. Sorry. This number right here is off by. Guys, sorry guys. I'm right here fucking shit up. Yeah, right there. That number is off by 0.1. All right. 0.1. All right. Because of this number. So what that means is that this number could be 15.4 or 15.6. Okay. Plus or minus 0.01. Okay. That's what we just read, and fucking a whole bunch of weird, complicated shit. I just want to know when we're going to be done with this book. I mean, this chapter. God damn, dude. All right, just 2 more pages. Yeah, good shit. Good shit. All right, let's keep going. And it's mostly words, so that's good. We just have to read. There you go. Kind of representation of very common experimental work. In this book, however, we'll use significant. Let me check the focus on the camera. We use significant figures to represent uncertainty. In science, they'll say significant figures. In math, they'll say significant digits. And whatever they say, they'll say significant some shit. All right. Anyways, in whatever book or field you're in. Anyways, note some numbers are exact, which no uncertainty whatsoever. 3 examples are the number in meters, and a kilometer is exactly 1,000. The speed of light defined to be exactly 299 million. Wait, no, yeah, 299,792,452 meters per second. As we learned in section 1.3, and the value of pi, the value of any measured quantity, however, will have some uncertainty. Scientific notation is helpful in representing the number of significant figures in a measurement. When we say that the radius of the moon is equivalent, the radius of the moon at its equator is 3,476 kilometers, we imply that there are 4 significant figures in the value that the uncertainty in diameter is only about 1 kilometer. Since there are 1,000 meters in 1 kilometer, we could also say express the diameter is 3,476,000 meters. This is misleading, however, since it is given the impression that there are 7 significant figures in the value. That is incorrect. We do not know the value of the moon equal or equatorial radius, some shit like that. Equatorial radius in within 1 meter. A better way to express the diameter in meters is as 3.476 times 10 to the 6 meters, which makes explicit that there are only 4 significant figures in the value. The radius of the minor planet Aries is less than well known and is about 1,300 kilometers. Only the first 2 digits are significant, so it's more accurate to express the dimensions in 1.3 times 10 to the 3 kilometers. There are special rules to help determine whether or not zeros in the number are significant. Leading zeros are not significant, so the number 003, could you guys see also? So the number 0.0035 has only 2 significant figures. Trailing zeros to the right of the decimal point are significant. So the number 0.3500 has 4 significant figures. When we have trailing zeros to the left of the decimal point, as in 350, things get ambiguous. To make it clear that the trailing of the decimal point, as in 350, things only get ambiguous. To make clear that the trailing zero is significant, the best to write is 3.50 times 10 to the 2. We will attempt to do just that throughout the text. However, there are many times when it is more expedient to write the exact numbers without scientific notation. For example, there are exactly 60 seconds in 1 minute. So there is 60. So the 60 has many significant figures as we need, and we won't bother writing minutes, so that 60 has many significant figures, so we wouldn't bother writing 6.0000 times 10 to the 1 or 60.000 to indicate whether the value we have significant figures. 36,000, you should assume that the trailing zeros are significant. So what is it saying? I know that's some confusing shit. All right, get the number 350. Any number 350. This only has 2 significant figures. All right. And then if you want to have the third one to be significant, you put a fucking 0. Put a decimal point. You see that? I think that's what it's trying to say. And then, but on the book, what they're gonna say, to have three significant figures is they're just gonna write it out like that, times one, two, times two. All right, that's all it's saying. Mind explosion. Yeah, so for sure, that's why I'm reading, and then I'm just gonna clear shit up, because sometimes I'm reading also and I'm like, what the fuck? And then you just gotta think about what exactly is it saying. Oh, and then the second part that it was saying is, when it's some shit that's exact, like seconds, like you know how 3600 and 60 seconds, when it's actual conversion units, even if it's a one, or if it says 1 over, oh shit, let me draw a different, 1 over 36 and 7.54. All right, this is the uh exact conversion to whatever the fuck you're plugging in, okay? Making it up. All right. So no matter what, this means 4 sig figs, okay? I mean, no matter when it's a actual conversion unit, don't worry about the sig figs, okay? Because those are whole numbers, all right? Whole representations, okay? So don't worry about that shit. That was the second half of whatever the fuck I read. All right, so let's keep going. There are special rules to help determine whether or not zeros are in the number are significant. The leading zeros are not significant, so the number 0.035 only has two significant leading numbers that are not significant. Trailing zeros to the right. Wait, I think I already read all this. Yeah, I think I already read this. In most problems in this book, in most problems in the book, you might be asked about the motion of an ostrich that runs 43.9 meters, three significant figures, 2.3 seconds, two significant figures. If we use your calculator, you'll find the speed of this ostrich and the distance traveled by the elapsed time, and the result will be 43.9 divided by 2.7 is equal to meters per second, 19.086 something. Incorrect. Okay. All right. This answer is incorrect because there are not 10 significant figures in the answer. In no way do you know the rest of the precisely. The general rule for multiplying or dividing numbers is that the result has the same number of significant figures as the input number, with the fewest significant figures. In our example, the elapsed time of 2.3 seconds has fewer significant figures than 2. Then the distance of 43.9, the result has only two significant figures. Rounding our result, we get 19 meters per second. So basically, just uh, whatever the small number is of that we know for sure, the final answer better only have the fewest amount. Which right here in this situation, it's 2. Over here, we gotta make sure it's only 2. Okay, that's what it's saying right there. I think I'm almost done. Damn, dude, I'm already tired of reading. I'm already call it quits already. Dimensional analysis. All All right, let's just fucking muscle through this shit. All right, so reading. All right, following the same rule is a strip of cloth 35.65 centimeters long and 2.49 centimeters wide. The area length and width has only three significant figures: 35.65 centimeters, 2.49 centimeters, 88.767 centimeters squared, around to 88 centimeters squared. There's a slightly difference rule for adding and subtracting numbers. Suppose that there you drive 44.3 kilometers according to the odometer in your car from the central city to the parking lot of the Metropolis shopping mall. When you walk an additional 1.8 meters or 0.18 kilometers according to your pedometer on your favorite clothing store. The total distance you have traveled is 44.3 kilometers plus 0.108 kilometers, according to your calculator, is 44.408 kilometers. This isn't quite right, however, because you only know your driving distance to the nearest tenth of kilometer, resulting you should round to nearest of the nearest tenth of the kilometer, or 44.4 kilometers. So sorry guys, this shit's fucking boring for me right now. I'm already getting tired of just reading this shit. Look to where our problem. We're gonna solve the problem of the moon, and then we're out of here. All right. So one digit to the right of the decimal point. So, anyways, guys, I feel like skipping all this shit, honestly, and just go to. I guess I gotta read this shit. All right. Thus, the general rule for adding and subtracting numbers is that the result we have no less in uncertainty than the most uncertain input number. Than the example. That's that 44.3 kilometer distance, which uncertain is about 0.1 kilometers. Stated in another way, the answer may have more digits to the right in the decimal point than the input number of the fewest digits to the right of the decimal point, and all the numbers are expressed in scientific notation with the same exponent. Let's summarize the general rule. When multiplying and dividing numbers, the result should have the fewest number of significant figures and the input number of the fewest significant figures. Apply to some shit. Rule number 2, when adding and subtracting numbers, resulting should have the same number of digits to the right of the decimal point. I support you, camarada. Do your thing. Thank you, bro. Just because of you, bro, it makes me feel. You give me the energy to keep going, bro. Because I'm already fucking exhausted, bro, and I'm already done with chapter 2, dimensional analysis. I just got to finish this because I'm already on chapter 2. After those 2 pages, yeah. Yeah, see, I'm on chapter 2, and then it finally gets good. Sorry, bro. Just like I said, when we all go to class, bro, the first 2 chapters in chemistry and physics, bro, fuck, man. The longest days of the year. Like, we'll just leave it at that. Let's just say I read that. I think I did read that. All right, let's go to the problem. I rather do the problems than. I know most people, when they read it, they skip the problems and they just read the words, but you only grow by reading by doing the problems. All right, hopefully you guys could read it also. So I'm gonna read it and then we'll pull out the problem. All right. So, what is the volume in cubic kilometers of Earth? What is the volume of the moon? What is What is the combined volume of the two worlds together? The radius of the Earth is 6,378 kilometers, and the radius of the Moon is 1,736 kilometers. All right, so they gave us two numbers. All right, so the Earth is equal to 6,378. Oh shit. All right, so the Earth, they gave us a few numbers, right? Let's put this one up first. 3.78 kilometers. All right, is the radius of the Earth. We'll call it R, and then for the Moon, the Moon's radius is 1,738 kilometers. All right. So the question is in cubic kilometers. Cubic means a cube. You know what I mean? How many cubic kilometers? What is a volume of the Earth in kilometer? Wait, in cubic kilometers, and what is the volume of the Moon, and then what is both of them combined? Okay, but first we got to figure out what the fuck is a radius. All right. So what is a radius on a circle? So if you get a circle, the distance between the center of the circle. All right, so the distance between the center of the circle and to one of the edges is called the radius. Right here's the radius, all right? And then if you get the same circle and you go all the way across, that's called the diameter. All right? You see that? So and then we got another formula for what's it called? Volume. So to figure out volume, you're going to have this formula called 4 pi r squared, or r cubed actually. 4 pi over 3. Yeah, 4 pi over 3. Over 3, all right? So this is how you figure out the volume of a fucking sphere, all right? If I remember correctly, okay? So this is how you figure out the volume of a sphere. 4 pi r cubed over 3. So that's why all those fucking flat earth motherfuckers, this is like their kryptonite. Go take this equation or this shit to one of your flat earth fuckers, and they're not gonna know what the fuck to tell you. You're gonna be like geometry and all this shit. I don't know what the fuck. But volume is basically the amount of space within a sphere. Okay, this is the equation of a sphere and a volume of a sphere. Okay, if I remember correctly. So anyways, let's go in there and start plugging shit up. All right. So the radius, see, they already gave us the radius right here on both occasions. So I'm just gonna plug it in. Okay. I'm trying to figure out if that's right. 1,007. Yeah, I'm right. I'm right. I'm right. I'm right. All right. So basically, remember that the volume equation. What was it? 4, and then pi is 3.1415. I just remember that shit. All right. But on the calculator, I think some calculators just say pi. All right. And then times r. They gave us r. and then cubed over 3. All right. And then all we got to do is just plug in both numbers. So the one of the numbers for Earth, what was it? For Earth is 6378. 63. Oh shit. 78 kilometers. That's for the Earth. Okay. Damn. Should I put an E or some shit? KME. So it stands for kilometers of Earth. And then the other number, what was it? 1738 kilometers of the moon. All right. So there's 3 problems right there. Okay. So to solve this, just plug it into your calculator. So, man, I don't know how I should do this with you guys. Hopefully, I think I don't know if I'm confusing you guys with that shit. Hold on. Let me do something real quick. Then 4 pi 3.1415. What was the other number? Kilometers of the moon. All right, there you go. All right. Oh shit. Over 3. All right, guys. So here are the 2 numbers. So for Earth, when you plug it in, cubed. Shit. Hold on. All right. So when you plug both answers to the calculator, you're gonna get for Earth, you're gonna get 1.08 times 10 to the 12. And then for the moon, you're gonna get 2.19. It says 2.19999, and then for the first one was 1.086. Hold on, let me just write it. 867, and then up here will be 1.990 times 10 to the. I think it says 10 to the 10 kilometers. Shit, I'm running out of space. All right, 10 to the 10 kilometers. All right, so these are both of the answers. And then to get both of them combined, all you got to do is just add them up. So that'll be 1.08 times 10 to the 12 and 2.19. You know what? I'm just going to carry that 6. 199 times 10 to the 10. Add those up. All right. So when you add those up, you're going to get 1.108 times 10 to the fucking 12 kilometers when you combine the Earth and the moon. Okay. And let's go check. Let's go check if we're fucking right or we're fucking wrong. There's the next page. So everything we just did right there, they did it also right there. You see that? So the volume the volume is 4 pi 6378. Oh yeah, I did the I did the problem on the last page right there. When I was in the university, it's right there. That's how I knew the answer, just because I was 1.08, and since my calculator doesn't fucking work, or I don't have a calculator, I just use the numbers right there. But I'm showing you how to get the answers. All right, because it's more important to know how to do it rather than actually having the fucking answer. Because see, look over here, you could just go and double check it. See that's the work how they did it. It's basically the same shit we did. Just plug in the fucking numbers. All right, and it's that easy. Oh, I forgot cubed on the final answer is supposed to have a cube. Okay. Oh my god, my foot's falling asleep. Okay, dimensional analysis. So we're almost done with this chapter, and we're out of here. Ah, fucking camera. Great. Hold on, guys. Can you guys hear me? Okay. Oh man, my foot's falling asleep. All right, let's finish this real quick and we're out of here. All right, we're in dimensional analysis of this chapter 1.5. So, dimensional analysis is a powerful way to check the results of physics calculation. Once you've done a problem, it is useful to be able to quickly determine how likely it is that you've done the problem correctly. One valuable approach is to do dimensional analysis. This approach is particularly useful when we calculate the algebraic result and want to check it before substituting numerical values. You know, let me get the screen off right there real quick. All right, we're almost done out of here. This is the last page, and I think we're out. Yep. We just got to read the words and we're out of here, guys. Thank you for watching this video. It was a 2 hour and a half and some change. But we're out of here. All right. To see what we mean, first note that any physical quantity has a dimensions. 3 quantities that we introduced in section 1.3 are mass, length, and time. Table 1.1 and section 1.3 lists additional physical quantities that we say the mass of a hydrogen atom has dimensions of mass and the diameter of the atom has dimensions of length, and the amount of time it takes the light to travel in a diameter has dimensions of time. Mass, length, and time are fundamental dimensions because they cannot be expressed in terms of other more fundamental quantities. We'll encounter a few other fundamental dimensions in later chapters. Dimensions have units, but are not units themselves. Units are used to help express the numerical value in dimensions. A dimension is the length may be expressed in units of meters, or examples of length of a typical house cat is 0.65 meters. The dimensions of time is expressed in units of nanoseconds, and dimensions of mass might be expressed in units of kilograms. The dimensions of many quantities are made up of combination of fundamental dimensions. One example is speed, which is dimensions of distance per time, or distance time for short. Another is volume, which has dimensions of distance cube or distance cube. Here's the key to understanding dimensional analysis. In any equation, the Fuck, guys, this might sound some weird shit, but I thought there was somebody sitting on the fucking couch right now next to me, moving and shit. That's some crazy shit. Anyways, for example, suppose you equation of dimensions must have this. Here's the key to using dimensional analysis in any equation. The dimension must be the same or both sides of the equation. As an example, suppose you hold a ball of height h above the ground and let it fall. The ball, it takes time to reach the ground. You'll calculate the relationship between height h and the time t is h equals v t squared, where v is the speed of the ball just before it hits the ground. Is equation 1.2 dimensional correct? You'll find that replace the symbol by the dimensions of the quantity, that is the distance, time, then t and dimensions. We cancel on just the algebraic equation with simplifying, and we get distance is equal to distance over time times time squared times time multiply distance times time. This is inconsistent in the left-hand equation. H dimension, some shit. Within the higher r v squared, the dimension of the distance multiplied by time, so the equation 1.2 cannot be correct. And it turns out that the correct relation between the height and the ball and the drop, the time h hits the ground, is h is equal to 1/2 g t squared, where g is a constant. When the dimensional analysis figured out the dimensions of g, h is the distance of t and the time, and 1/2. Sorry, guys, I'm reading right there. I got tired of reading all this shit. But that's what I'm reading right now, and it's freaking hard for me to read that because I really don't feel like reading it. But basically, it's saying how to figure out time. I mean, this relationship right here and all that. Where B is a high distance, some shit. The SI unit of G must then be in meters per second squared. We'll learn the significance of the quantity G called acceleration due to gravity in chapter 2. All right, perfect. All right, guys, we're out of here. We finished this. Dimensionalized cannot tell you everything. Suppose we're reading a little bit on the corner right there. Suppose the result algebraic we failed to include that 1/2 is the 1/3 found GT dimension. So dimensional analysis determine whether the results could be correct. Anyways, guys, it's just a whole bunch of shit. Well, we're on chapter 2 and we're out here, guys. Thank you. This was a long ass video, 2 hours and 43 minutes. God damn. Wow. That's a long shit. So our chapter 2, linear motion. And finally we get to something good, guys. Oh man. That was some shit. All right. We're out here. Sorry. Oh, Benny right here. Thank you, Benny. Quantumania. Buenas noches, big dog. All right, Benny the Cali, thank you, bro, for sitting through this shit, bro. I really appreciate everything that you're doing and all the support, bro. Much love. And if you're Raza and you want to learn this, or anybody want to learn this, please tag along. And remember, guys, I developed my own branch of mathematics, and we don't get to it. Well, we're getting to it pretty soon. I might just. Sorry, I've written some shit in this book that's private intellectual property, and I don't want to like share it, so I am gonna like skim through it and make sure I don't highlight them live with you guys. But I'm gonna show you guys my own way of solving shit, and I developed my own thing that's based with chemistry and physics, and we're gonna solve chemistry and physics problems at the same time using my method, and it's not found anywhere and all that shit. And I'm gonna be the one showing you how to do it. So when you go to the classroom, you go in there and fuck shit up. So fuck the teacher and professors, all that shit. tear the ass of all of your students and everybody in the class and all that shit. All right. So that's what I'm gonna be teaching you guys. That's why originally I was gonna teach you guys chemistry first and then the physics, but we're gonna do both at the same time. All right. So next time we're gonna do chemistry. Or actually on the next video, make sure you click on chapter 2 of the physics. All right. But make sure you check out the chemistry series also. All right. At the same time. But anyways, much love, and I'll see you guys next time. All right. And I see Benny, thank you, bro. I mean, Benny the Cali, thank you, bro, for tagging along, bro. And I didn't know that you knew this shit too, so that's pretty cool. But anyways, much love to everybody joining, and I'll see you guys on the next video.